Yeah, I changed the title a little bit. I think inside the abstract they say for all FEM, but since my experience is more in fluids, I had to put that in there. And I was going to talk all about the homotopy solvers and the different homotopy solvers we have, but I realized I didn't implement these in a 20-minute talk. I'm not going to be able to convince you of what I know very well. So I'm just going to give you the argument for why I use these, and hopefully generate some discussion about how we actually solve our fluids equations and things like that. So this is just 3 parts: general plans, nonlinear woes, and why I don't like nonlinear equations, and homotopy solvers, maybe a hope to experiment further. So in my experience, when I want to solve some sort of system, I give some sort of problem, I always tend to start at some small level. For example, in fluids, your basic level, you start with these Stokes equations. And you have a whole bunch of different ways of going through the Stokes equations. Then you have something like Navier-Stokes or something else that maybe describes something a little bit better, describes what you're working with a little bit better, and the idea comes through, but you have quite a few more worries. Then we get to Newtonian fluo, which I've been working with for the last year or so. That really is the equations I want to solve at the end of the day. But as anybody who's ever opened, I lost the name. Any rheological book, you'll find that there's a whole heck of a lot of these different models, and they all have different philosophies and religions behind why they're good and why they're bad. So you don't really know which to use, but they all kind of sit on top of these things way down there. And if you don't get those right, you don't have any chance of getting these right. But a lot of people go ahead and work on them anyways. And then you want to couple it with something. You actually want to solve a real-world problem, whether that be drag or biofilms or mixing or anything like that. And sometimes we actually want to use what other people's used as well, done as well. So it becomes a really large problem. And as you can see, it kind of becomes like this stack of lots of different problems to work with. And my general kind of work has been, right now, I started with a grade 2 algorithm, and I wanted to do a fluid-solid interface in a lung. I didn't get there because I got to here, and I realized I wasn't really solving things very well. And I asked other people how they solved them, and they told me, well, we don't do it very well either. So I'm going to talk a little bit more, especially about grade Oldroyd B and why we don't solve it very well. And then if you're interested, I can talk about why we don't solve some of these others very well, or why it doesn't really matter if we do solve it well. So just to start out with the Oldroyd B model, I realize that some people might not be familiar with it. More or less, it's just a model based upon polymers that you use as Maxwell solids, and basically you have a Hookean elastic or a Newtonian flow based upon this parameter lambda. And you generate a constitutive equation that looks roughly like this. This is a formulation from Bayesian's. He has a very nice review article, and he classifies all these different models that you see at the bottom on these kind of idea where you have an upper convected Cauchy stress, and you have some nonlinear function here. But largely, everybody works with this lambda, and you have quite a few different things that come out. The convective stress. When lambda gets larger, you have quite a few nonlinearities that come out based upon the convective stress. And so it's gone from 50 years, 1950 when this was Oldroyd seminal work was developed, to some decent algorithm, some decent 2D algorithm. There's much debate as to whether they even have solutions that exist for these things in 3D. I mean, engineers will compute them sometimes, but mathematicians don't believe them, so it's whatever your particular bent is. And in that time, they kind of went for there's been two main kind of themes that worked with not dealing with the nonlinearities. If we strike out the nonlinearities for now, and we just look at why it doesn't work when we have very low, what they call Weissenberg numbers, or very low lambdas. And I like to think of it as there's two kind of areas inside each one of these. You have a discretization or a model rewrite. So for example, hyperbolicity, all the advection stuff, we can either rewrite our discretization, as done with Markov and Crochet's super elements, and or Fortin's discrete or discontinuous Galerkin formulation. You can also, or you could do some sort of stabilization techniques on top of that, as done by these guys as well. And also, at the end of the day, there's also coupling fields. So there's quite a few fields you're coupling here. And so they have the same kind of thing, where you either discretize differently, or what these guys do is they split out the different types of stresses. Okay, so that took quite a while to get right. But the big thing that kind of nobody's really done well, and they realize they haven't done it well, is this actually giving a nonlinear solver. So every one of these papers starts out, every method starts with some Picard iteration. Picard iteration is nice, it's easy to code up, it's not very effective once you get into high nonlinear problem or larger nonlinearities. But if you're just working with the small nonlinear factors, it's okay. Then you see people come along with the Newton-Raphson methods, and everybody just kind of says, oh, just use Newton-Raphson. And the nice thing about it is it appears to work, but you don't know anything about your solution space when it appears to work. You get an answer, and papers will literally tell you, my solution worked because Newton-Raphson converged. They won't say, and if it doesn't converge, they say, oh, this isn't a good algorithm. Okay, so certainly not a good algorithm if it doesn't converge, but if it converges, you have no guarantee of what your solution space looks like at all. And then they came along and made it faster by using some preconditioned GM-res, and this is what I call the decent solver, the things that can solve larger problems. And all of these solvers really require some continuation methods. They don't always work on all meshes, and it's just kind of a whole area of different problems that come up. But that's what we got, that's what we go with, and if you want to get more things going, you use these methods. Johan?
Is this time independent?
So I'm mostly working, with time independent. I've been working with, all these were creeping flow, like 2D, very simple models, but certainly there are people who do more other types of stuff, and my colleague Todd DuPont will tell you, well, you shouldn't even use 2D because it doesn't make sense in a fluid anyways, but there's a little bit of where do you start in this as well. What we kind of started doing in the last 6 months with Matt and I especially, started looking at alternate solvers. Because we want to know, one, is it the case that these Oldroyd B models have one solution? It's very hard to determine using Newton, and even if you do a parameter search around all the different types of continuations and lambda values, it doesn't really show you anything. It shows you that you can, if you come to one solution every time, it shows that you have a good solver to get that one solution. It doesn't show you that there's a lot of what the full solution space looks at. And so we wanted to use different methods that might give us more of these. And these homotopy solvers, which is a polynomial solver using homotopy continuation, will compute all solutions. Now, all solutions is kind of a big number sometimes, because it can go, it's 2 to the n, where n is the number of equations, so it can get quite large to find all these solutions. But we can also attach things that we've done in the past, such as multi-grid methods and nonlinear Gauss-Seidels.